Hi, I am Raghavan, Chemistry faculty from All Force College. I welcome you all for the All Force Chemistry e-learning classes session 34. Okay, in this session we are going to discuss about anomalous electron configuration of chromium and copper. Anomalous electron configuration of chromium and copper. That is, in the last session we completed Hund's rule of maximum multiplicity, and along with that we have done anomalous configuration of chromium is completed. Okay, so now we are continuing with chromium and copper. Today we will take up, okay, anomalous configuration of chromium, 24 atomic number. Okay, so that is the normal configuration we explained. That is, in the last session we explained the detailed configuration of chromium. Okay, and normal configuration appears like 4s2 and 3d4. Okay, and the deviation from the normal configuration, that is anomalous configuration of chromium, is argon 4s1 3d5. 4s1 3d5. Since according to the significance of the Hund's rule of maximum multiplicity, that is half-filled d orbitals are more stable, therefore in order to acquire extra stability, chromium shows deviation from the normal electron configuration. Okay, so therefore always you should remember that what is the electron configuration of chromium 24? It is always 4s1 3d5. You should not say that 4s2 3d4. It is always 4s1 3d5. And in the last session we also explained, so why this 4s1 3d5 is more stable? Because of more number of exchange pairs and exchange energy. Okay, that we explained in the last class, in the last session only. Okay, now that is chromium 24 is completely explained in the last session. Now today we are going to take up, so copper 29. Okay, copper 29. Copper atomic number is 29. In this copper atomic number 29, the electron configuration, normal configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d9. So it is 4s2 3d9. That is a normal electron configuration of copper. This is normal electron configuration. Normal electronic configuration of copper. Okay, so it has 4s2 3d9, 4s2 3d9. This is 4s2 3d9 configuration of copper. 1 2 3 5. So 3d9, 1 2 3 4 5 6 7 8 and 9. So it has 3d9. Now according to the significance of the Hund's rule, the s electron is transferred from the 3d orbital, that is transferred from 4s orbital to, it is transferred from 4s orbital to the 3d orbital. So therefore it becomes 3d10, that is 4s1 3d10. 4s1 3d10. This is stable electron configuration of copper atomic number 29. So always we should remember that copper stable configuration is always 4s1 3d10 completely filled d orbitals. Okay, so this is the anomalous electron configuration. That is, what is the meaning of anomalous electron configuration? That is deviation from the normal electron configuration. Okay, so normal configuration is 4s2 3d9 and anomalous configuration is 4s1 3d9. Why the deviation takes place? In order to acquire stability. So which rule explains the stability of anomalous configuration of copper? So that is Hund's rule explains the anomalous configuration of copper chromium. Okay, and one more example let us take up. So we completed the two. Chromium 24, it was completed in the last class, in the last session, along with detailed, that is exchange energies we completed. Today we revised that in short. Okay, and we have taken copper. So in this copper, so 4s1 3d10. Okay, 4s1 3d10 is the stable configuration of copper. Now, palladium atomic number 46. Palladium atomic number 46. That is important for the objective examination only. Nobody will ask you in the IP part. Okay. That is for IP part examination is chromium 24 and copper 29. These two are important. Now, palladium atomic number 46. So, the normal configuration of this atom is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2 and 4d8. This is the normal electron configuration of palladium 46 atom. Okay. Now, in order to acquire stability, that is for the complete filling of the d orbitals, the two s electron, the valency 2 5s electrons are completely transferred into the 4d orbital. That is the 5s orbital, 5s2 electrons is completely transferred into the 4d orbitals. So therefore, the 4d orbitals are become completely filled. That is called fully filled. Okay. The 5s orbital remains 0. Now all the 5d orbitals are completely filled with electrons. That is what is the configuration of that is palladium 46. The palladium 46 configuration is 5s0, 4d10. Remember. Okay, the number of s electrons in the valence shell of palladium 46 0, because all the 2 electrons are transferred into the 4d orbital to acquire completely filled and extra stable configuration of that. Okay, so that is 5s0, 4d10. This is another important, this is purely important only for your objective examination point of view. Okay, whereas in the previous chromium 24 and copper 29, that was 2 examples, important even for your IP part as well as your objective part. Okay, right. So this is anomalous electron configuration is completed. Anomalous configuration of the elements is done. Okay, next concept is Paulis exclusion principle. Okay, Paulis exclusion principle. What is the statement of Paulis principle? Statement of Paulis exclusion principle. Paulis exclusion principle. What is the Paulis exclusion principle? What does it state that? Yes. See, for example, helium atom. Helium atomic number is 2. The configuration of helium atom is 1s2. So the s orbital being it contains only one orbital, it has got 2 electrons in that. Now for these 2 electrons, that is 2 electrons of the orbital. So what is the principal quantum number value for this 2 electrons? The 2 electrons belongs to the s subshell of first orbit. Okay, so the 2 electrons belongs to the s subshell of first orbit. So n is equals to 1. Okay, the principal quantum number value for that 2 electrons, for these 2 electrons, n is equals to 1. Yes. Next, these 2 electrons are present in s subshell whose L value is 0. Okay, and these 2 electrons belongs to s subshell and whose magnetic quantum number value, that is orientation value, is also 0. And remember, these 2 electrons possess similar, that means same, n, L and m values, but these 2 electrons differs in spin quantum number value. Okay, so one electron has a clockwise spin, for which we have the spin orientation value is plus half. The other electron is anti-clockwise and its spin orientation value is minus 1/2. So the 2 electrons belongs to the orbital having different spin quantum number values, but these 2 electrons possess the same principal quantum number, azimuthal quantum number and magnetic quantum number values. Okay, so now what is the statement of the Paulis principle? No 2 electrons of an orbital, no 2 electrons of an orbital no two electrons of an orbital can have all the 4 quantum number values identical. That means the 2 electrons belongs to the orbital, they possess similar n, l, m values, but the 2 electrons belongs to the orbital, they differs in spin quantum number value. They differs in spin quantum number values. Okay, once again, statement of Paulis exclusion principle. No two electrons of an orbital of the same subshell of an atom, no two electrons of an orbital of the same subshell of an atom can have the same set of 4 quantum number values identical. Is it clear? So, the 2 electrons of an orbital of the same subshell possess the same principal quantum number, azimuthal quantum number and magnetic quantum number values. The 2 electrons differs in spin quantum number values. Okay, so that is a statement, and here we explained example. Okay, the 2 electrons of helium belongs to the s subshell. Okay, therefore for these 2 electrons principal quantum number value is 1, and for these 2 electrons azimuthal quantum number value is 0, and for these 2 electrons the magnetic quantum number value is also 0, and these 2 electrons differs in spin quantum number values. Okay, they differs in spin quantum number values. Okay, that is fine. Now, in an orbital, according to this configuration, how many spin values are allowed? Yes, according to this example, we can explain that, yes, that is in an orbital, maximum 2 spin quantum number values are allowed. Maximum 2 spin quantum number values are allowed. Okay, one is plus of, the other one is minus of. So, as the experimental results are showing that an orbital is allowed with only 2 spin quantum number values, therefore, Paulis principle can also be stated as, Paulis principle can also be stated as an orbital can accommodate maximum of 2 electrons only. What is that? An orbital can accommodate 2 electrons only. Can accommodate 2 electrons. 2 electrons only. Can accommodate 2 electrons only. That is Paulis exclusion principle can also explain like this. Now once again, let me repeat. So the definitions of that is statements of the Paulis exclusion principle. Okay, no 2 electrons of an orbital of the same subshell of an atom can have all the 4 quantum number values identical. The 2 electrons belongs to the same orbital possess the same principal quantum number, the same azimuthal quantum number value and same magnetic quantum number values, but the 2 electrons belongs to the same orbital differs in spin quantum number values. They differs in spin quantum number values. Now, according to this, as the 2 spin quantum number values are allowed in the orbital, therefore, Paulis principle can also stated as an orbital can accommodate maximum of 2 electrons. Can accommodate 2 electrons only. That means maximum of only 2 electrons. That is the Paulis principle. Okay, statement and explanation is done. Okay, now let us discuss about, suppose if Paulis principle is not known to us, so then what is the electron configuration of lithium atom? Okay, so Paulis principle, that is the detailed explanation is completed. Okay, anomalous configuration is completed, and we completed Hund's rule of maximum multiplicity in the last session, and before that we completed Aufbau principle. Okay, now if Paulis principle is not known to us, Okay, if Paulis principle is not known to us, then what is the electron configuration of lithium atom? Lithium atomic number 3. Okay, so the options, let us see. Options is, first option, let us say 1s2, 2s1. Second option is 1s3. Third option is say 1s1, 2s2, and fourth option say it is none of this. Okay, what is the question? If Paulis principle is not known to us, then what would be the electron configuration of lithium atom? So according to Paulis principle, we can understand an orbital can accommodate maximum of 2 electrons. If it is not known to us, then the orbital may accommodate any number of electrons. So therefore, all the 3 electrons may enter into the same s orbital, that is 1s orbital. Therefore, this will be the answer for that. Okay, when Paulis principle is not known to us, then all the 3 electrons get enter into the same orbital, because there is no limit for that. Okay, so the answer would be like this. Okay, so like that we can expect the questions. Now let us experience some other questions, like the electron configuration of the nitrogen atom. Electron configuration of nitrogen atom, atomic number 7. Okay, 1s2, 2s2, 2p3, 1s2, 2s2, 2p3, 1s2, 2s2, 2p3. This is 1s2, 2s2, 2p3. Okay, that configuration is okay, fine. So 1s2, 2s2, 2p3. Okay, this is 2p3 configuration only. So then this configuration violates. What is the principle it is violating? This configuration violates, first option, Paulis principle. Paulis principle. Okay. Second option, Aufbau principle. Aufbau principle. Third option is Hund's rule. Okay. Fourth option, uncertainty principle. Uncertainty principle. Yes. So Paulis principle, Aufbau principle, Hund's principle or Hund's rule, uncertainty principle. So this configuration of nitrogen is violating the principle. So that means the electron configuration according to the Hund's rule. So Hund's rule states that the pairing of electron takes place when all the degenerated orbitals filled with 1 electron each, then only the pairing should start. Okay, that means all the p orbitals must be filled with 1 electron each, then only the pairing starts. So it is not following the Hund's rule. Answer is Hund's rule. Okay, according to the concept of Hund's rule, pairing of electrons takes place only all the degenerated orbitals filled with 1 electron each of parallel spin, then only the pairing starts. So this is against to the Hund's rule. Okay, so Hund's rule is not followed by that configuration. That is fine. Okay, next let us experience with some other examples. Even let us complete the magnetic properties. Okay, then after that we can explain the other examples. Magnetic properties. Magnetic properties. What are magnetic properties and how they are classified? Magnetic properties of the elements. Okay, magnetic properties are classified basically into 3 types. Okay, there are so many types are there. So now we are taking only the major classification, that is, one is diamagnetic, Next one, paramagnetic, and last one is ferromagnetic. Okay, ferromagnetic. So what is the meaning of diamagnetic? When a substance is kept in the magnetic field, the substance is not attracted by the magnetic field. Means what? It is not attracted means what? It may be repelled. Okay, because of not attraction. Not attracted means it is simply, we can say it is repelled. Okay, the substance, the species, that means the compound. The substance is not attracted by the external magnetic field, is repelled by the external magnetic field. The nature of the substance is called diamagnetic nature. This diamagnetic nature is due to the absence of unpaired electrons. It is due to absence of unpaired electrons. Absence of unpaired electrons. What do you mean by absence of unpaired electrons? The orbitals may be completely filled or the orbitals may be vacant. Okay, orbitals may be completely filled or orbitals may be vacant. Okay, orbitals are completely filled or vacant. Completely filled or they may be vacant. So that means what? Absence of unpaired electron, that is unpaired electrons is absent. That is why it can cause a diamagnetic nature. What is the diamagnetic behavior or diamagnetic nature of the substance? The substance which is not attracted by the external magnetic field, or we can say rather the substance is repelled by the magnetic field or electric field. The behavior is called diamagnetic nature. Okay, or diamagnetic behavior. It is because of absence of unpaired electrons. That is the main point you have to remember. Okay, what is paramagnetic nature? The substance which is weakly attracted towards external magnetic field, weakly attracted or feebly attracted towards external magnetic field, feebly attracted or we can say weakly attracted towards external magnetic field is called paramagnetic nature. Okay, it is due to the presence of unpaired electrons. That is important point we have to remember. It is due to the presence of unpaired electrons. Okay, what is the concept? What is paramagnetic behavior? Yes, the paramagnetic nature of the substance which is weakly attracted towards external magnetic field or feebly attracted towards external magnetic field is called paramagnetic nature of the substance. It is due to presence of unpaired electrons. That is an important point for us. Presence of unpaired electrons. Okay, due to the presence of unpaired electrons, so the substance is weakly attracted. It is attracted towards the magnetic field. Okay, now here only let us calculate. See, the magnetic behavior, the magnetic nature of the paramagnetic substances can be calculated. The magnetic nature of the paramagnetic substances can be calculated using the following relation. Mu is equals to, the magnetic nature is equals to under root n into n plus 2, okay, n into n plus 2. So the magnetic nature of the paramagnetic substances expressed in Bohr magneton units. That is, what is Bm? Bm is nothing but Bohr magneton units. Bohr magneton units. It is expressed in Bohr magneton units. Okay, so that is the magnetic nature of paramagnetic substances, the magnetic moment of paramagnetic substances can be calculated using this expression, using this equation. What is N? Where N is equals to number of unpaired electrons, number of unpaired electrons, number of unpaired electrons, number of unpaired electrons. Okay, so this is the important relation we have to remember. Okay, number of unpaired electrons N represents. Okay, this is about paramagnetic nature and how we can calculate the paramagnetic nature of the substance. What is ferromagnetic nature? The substance containing more number of parallel spin unpaired electrons, more number of parallel spin unpaired electrons, they are strongly attracted towards magnetic field. The behavior is called ferromagnetic nature. The substances which are strongly attracted, towards external magnetic field, the substance is strongly attracted towards external magnetic field due to the presence of more number of parallel spin unpaired electrons. Due to the presence of more number of parallel spin unpaired electrons is called ferromagnetic substance. Okay, that is ferromagnetic nature, and we have done paramagnetic, that is diamagnetic, paramagnetic and ferromagnetic nature is completed. Okay, so this is the outline explanation of the paramagnetic. So the important of this one is, among all them, so it is diamagnetic. It is due to absence of unpaired electron. Very simple to explain that. Then paramagnetic behavior. The paramagnetic behavior is due to the presence of unpaired electrons. Okay, that is fine, it is understood. Then how we can calculate that behavior? That can be calculated like this. Okay, that is nu is equals to, okay, under root n into n plus 2, where n is equals to what? Number of unpaired electrons, and the magnetic behavior, this property is expressed in Bohr magneton units. Okay, so let us work out some examples of this. Okay, that is the paramagnetic nature of the substances can be calculated using the expression, that is using the equation. Let us calculate some examples. Let us calculate. For example, let us take up scandium plus 3. Scandium plus 3. Scandium atomic number is 21. Okay, scandium atomic number is 21. Okay, what is the electron configuration of scandium? Scandium electron configuration. Okay, so that is 21. So how we can write the electron configuration of scandium? The electron configuration of scandium, that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. That is the electron configuration of scandium atom. Okay, that is the configuration of scandium atom. Okay, now we have to write scandium ion, we have to write. Okay, it is scandium atom. So 4s1, 3d, 4s2, 3d1. So this is like this: 1, 2, 3, 4, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. That is a configuration. Scandium plus 3 means this scandium atom is losing 3 electrons. So which electrons will be lost? So it is not from the, immediately it is not from the 3d orbital. First it is going to lose 2 electrons from the 4s orbital, then 1 electron from the 3d orbital. So therefore the scandium plus 3 has the configuration of up to this, because it is going to lose 4s2 and 3d1, all the electrons from the valence shell is lost. So then it has 1s2, 2s2, 2p6, 3s2, 3p6. All the orbitals are completely filled. 1s2, 2s2, 2p6, 3s2, 3p6. So all the orbitals are completely filled with paired electrons. That means no unpaired electrons are left. Okay, no unpaired electrons. No unpaired electrons. Therefore, Scandium plus 3 is diamagnetic. Because absence of unpaired electrons, it is diamagnetic. Diamagnetic. So we can express like this. Okay. Now let us calculate what is the magnetic behavior of Fe plus 3 or Fe plus 2. Let us say it is Fe plus 2. Fe plus 2, iron atomic number is 26. Iron atomic number is 26. 26 means, so what is the configuration of iron? So 1s2, 2s2. So here we can explain 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, okay, plus 6. So that is 3d6, that is normal configuration is 3d6. 3d6. So it is plus 2, means the iron atom has to lose the 2 electrons from the 4s orbital. Then it contains 3d6 electrons. Okay. So iron atom has lost 2 electrons from the 4s orbital. So what is the configuration of this? 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 is also present. Okay, because 4s2 electrons are gone, so they lost. So 3d6. How many electrons are there in the d orbitals? There are totally 6 electrons. So out of 6 electrons, let us see how many unpaired electrons are there. 1, 2, 3, 5. Okay, 3d6. 1, 2, 3, 4, 5 and 6. So it has got 4 unpaired electrons. Okay, 3d6, yes, 3d6 configuration we have given. So it has got 4 unpaired electrons. Now let us calculate magnetic moment of that. So it has got 4 unpaired electrons. Now magnetic moment of Fe plus 2, that is equals to under root n into n plus 2. What is the n? Number of unpaired electrons 4. So 4 into 4 plus 2. That is equal to Bohr magneton units. That is equals to 4 into 4 plus 2. 4 plus 2 is 6. 6 4s are 24. Root 24. Okay. Root 24 bm. Root 24 bm. Like that we can explain. We can calculate the magnetic moment of the paramagnetic substances. So first we have to identify how many unpaired electrons are present in that species. Okay. Fe plus 2 ion has 4 unpaired electrons. 1, 2, 3, 4 unpaired electrons. Okay. Based on that 4 unpaired electrons, we can calculate the magnetic moment like this. Okay. Next, one more example. Okay. Let us take up one more example. What is that example? Say nickel atomic number 28. Nickel plus 2 ion. Let us go with nickel plus 2 ion. Nickel plus 2 ion. Okay. Nickel atomic number is 28. 28 means the normal configuration becomes 28. 4s2 3d8. Normal configuration becomes 4s2 3d8. That is the configuration. Okay. Nickel plus 2 means the nickel atom has lost 2 electrons from the outermost orbital, outermost shell. It has gone. That means 4s electrons are lost. Then we have only 3d8. Now the configuration of nickel 28. Okay. So after losing 4s electrons, see what I mean to say is nickel atomic number when it is 28. So the normal configuration becomes in the valency shell 4s2 3d8. Okay, since it is a plus 2 ion means it has lost 2 electrons from the outermost orbital. That should be considered. Okay, it is not going to lose the 2 electrons from the 3d orbital. The 2 electrons are lost only from the 4s. That point you should remember. For that purpose only I am giving this kind of explanation. Okay, so now the configuration of nickel plus 2 is 1s2, 2s2, 2p6, 3s2, 3p6. 4s electrons are gone. 3d8. Okay. D orbitals contain 8 electrons. Now let us see the details of the d orbital electrons. Okay. The d orbitals are 5. 1, 2, 3, 5. Yes. D8. 1, 2, 3, 4, 5 according to Hund's rule. 6, 7 and 8. So 3 electrons are paired up and 2 unpaired electrons are left. Okay. So the nickel plus 2 ion has 2 unpaired electrons. Nickel plus 2 ion has 2 unpaired electrons. So therefore 2 unpaired electrons. Nickel plus 2 ion has 2 unpaired electrons. So the magnetic property of nickel plus 2 ion is equals to, so that is 2 into 2 plus 2. Okay, that is 2 plus 2 4, 4 to the 8, root 8 bm. That is the magnetic moment of the nickel plus 2 ion. Like this we can calculate. Okay, so it is not concerned with this. Okay, the nickel plus 2 is completed like this. Okay, next one. Next one is, say for example, oxygen. How many unpaired electrons are there in oxygen atom? Oxygen atomic number is 8. So how many unpaired electrons are present in oxygen atom? Unpaired electrons are 1s2, 2s2, 2p4, 2p4. So s orbital is always completely filled with 2 electrons, and this s orbital is also having 2 electrons, and the 2p4, the p orbitals are having 4 electrons total. So 4 electrons, let us represent the 4 electrons like this: 1, 2, 3 and 4. So oxygen atom has 2 unpaired electrons. Oxygen atom has 2 unpaired electrons. It has got 2 unpaired electrons. Okay, it has got 2 unpaired electrons. That is oxygen atom. Okay, now the number of unpaired electrons in sodium ion. Number of unpaired electrons in sodium ion. In sodium ion, let us identify the number of unpaired electrons in sodium ion. Sodium atomic number is 11. Okay, so sodium atomic number is 11. So that is 1s2, 2s2, 2p6, 3s1. That is 11 electrons. Now sodium ion, that means sodium always forms unipositive cation. Okay, so it forms cation only. So it can lose, it is going to lose 1 electron from the outermost shell, that is 3s electron. So the configuration is becomes 1s2, 2s2, 2p6. Yes, all the orbitals are completely filled. So that is why sodium ion has no unpaired electrons, we can say. Okay, like this we can identify the number of unpaired electrons, and based on the number of unpaired electrons, so we can calculate the magnetic moment of paramagnetic substances, like using, that is, what is the equation for that? Nu is equals to under root n into n plus 2 Bohr magneton units. Okay, using this equation we can calculate the magnetic behavior of paramagnetic substances. Okay, thank you.